So thank you, everyone, ladies and gentlemen. This is Bala speaking from Rollout IT. As for me, I'm a senior developer with 10 plus years of experience in web development background. And I'm also the founder and the CEO of Rollout IT. And today I'm very excited to hear more about Rust. I've been here in the first part. If you missed that, then we do have the recording. What we can share with you. Just contact us, or if you already registered, then we can automatically share both recording with you after this webinar. So just a few sentences about Rollout IT. We do end-to-end mobile and web development, and we do work very closely with our partners, mostly in Agile framework, to build cool applications, products. And we think having a community is really important. As well as the know-how sharing. So today, our speaker is Dávid Bíró, who is a senior web developer, having several years of experience in software development in JavaScript, TypeScript. And now he has a full-time Rust project at Rollout IT to build a customized, robust, and flexible mind map solution in Rust. So that's maybe the intro, and I hand it over to you, David, and I will share more in the chat. I don't want to keep you guys waiting. Cool, let's kick it off.
Today we will talk about two topics. One is traits, and the second is macro. There was a third topic, but the time isn't enough to talk about it. So threading will not be today. Okay, so let's begin with traits. I wrote a TypeScript interface here to let you see the differences between interfaces and traits, because they are very similar, I have to say. And I start right away with the problem with the TypeScript ones. So let's see, you have a class called foo, and you want to implement a show interface to foo. The only way to do that in TypeScript is write implement show and implement the methods, of course, that the interface provide. And the problem with this is that this foo is coming from another module, and if you are if you don't have an access for the foo class, then you cannot implement the show interface afterwards to it. So for example, this foo is coming from another module, and from our app, we want to implement it here. We cannot do that. But in Rust we can. For example, let's just write some quick examples, like having a foo struct, having a trait called, let's say, show, and it has a method called show. Okay, and let's implement show for foo. And if I save this, Rust will tell me that the show method is missing from the show implementation. And by just using control dot, I can fill the missing parts, which is very convenient. So we have this show method now, and just let's look quickly print line and say something like foo. And I save this, and this works. So if this foo is coming from a different module, there is no problem because we can implement still our traits here. Although there are examples when this is bad. For example, the foo method is coming from a package, and that package implements, for example, but no, that package doesn't implement a type, and by implementing trait to that type, that will be problematic because that could change the behavior of the package. So, for example, a standard trait like display, or actually this could be display, stdfmt display, which is used for printing structures. And let's implement it for foo. And Rust will not allow this if struct foo is coming from a different package. And this is, of course, a good safety feature again. Okay, let's move on. What else we can do with traits? Well, I cannot show you, or maybe I can. TypeScript and Rust both have generics. So there is, for example, from trait that is coming from the standard library. Let's just quickly make a struct again, foo, and implement from string for foo. And this is a trait which I can open and show you the implementation. This has a generic type parameter t that will be used for converting from a type t to another type, which in our case is foo. So if I implement this, and let's say, let's have foo some name, for example, which is a string. We have this string, so this will be the our data, for example, and this data will be used to create a foo. Or actually, this could be named, so I don't have to express it. And okay, no, it should work. So let's try out. When we have a string from something, then I can use the foo from string from something. And if I run this, this won't print anything. And there is also a problem, which is, yes, the fn main method should return nothing. So it is very similar that if I would write this, this means Rust is nothing. Not Rust is nothing. It means in Rust that it is nothing. So we should return nothing, and something is not nothing. So of course we cannot do that. So we have to close this line because the last line in Rust means returning something. So if I say this could work, and now if I run this, this will not show anything because I didn't print it out. And as you can see, the string also something also implemented for string, because if you see that this from is really the same from as the fools from that we just implemented. And that's because in Rust there are two types of string. One is static star reference, which is included in the binary that is produced by compiling the program. So when you compile this, you will be able to see this word exactly like this here. And this has some properties, like this is not mutable. You can access it, but this is not stored on the heap, so you cannot reallocate it. And you know, you can convert it to a string, which is a string stored in the heap. Heap is a place in the memory, and you can dynamically allocate memory for these types of types. And for example, vectors also use heap for storing items. So yes, static star reference cannot be used in here because we are using string, but of course we could use static star reference instead. But usually we don't use that because that will limit our application, because if I want static star and I don't need this, then I cannot pass real strings here. So dynamic strings cannot be passed to here, which is not a problem at all. But if we need to do that, we have to use real string. The size of the string is also different from the static star. Okay, that's enough, because today's meetup is not about this. And let's show something else. So we're back to the strings. We can also use into here. And okay, it looks like it needs to type in. Yes. So because we use into, well, I just write it quickly, and you will know that it is not really hard. Oh, well, yes. So this is from the from trait, where we have this string. What's the difference? Type annotations needed. Well, for the from method, there is no type annotation. And yes, because we need the foo here, and we don't need the type annotations there. We need the type annotations here. So, for example, if this is a string, let's call it, this is a name, which is a string, and we can use this into, and we can use this name here. No problem at all. So what is this into thing? Well, if I open it, you will notice that this is very similar to the from trait, but instead of converting from something, it is the opposite. And as you could see, if something is implemented, if something implements from, then it implies also the into trait. So for example, the string implements only the from trait, and because it implemented that, the something static star can be converted into a string, but this into is coming from this into trait. So you don't have to implement into manually into foo for string. And you could see that it is also working for foo. So for example, this will be a foo, and let's say name that into this would be a simple foo. And I have to add the type. Okay. So yes, it is working. And the way how they achieve this is very clever. I won't do this with from, but I instead create new trait. Let's call what will be show with the type parameter t. Is it what I want? Well, no. Let's just create a show trait, and this trait will just print line the. Well, if I make it to a method, so it will have an access to the self. So if I implement it to the foo, it will have access to the self. I can give the name here, for example, which here I cannot, but later on when I implement it, just let me close this quickly. And so let's implement the show for foo, and let's implement the missing members also. And okay, let's just print line with the name. It's very straightforward implementation. I can also say that this is a foo with name. And now I delete this one. And let's just try out. So for example, let foo equals to foo with a name which is a string. Well, I can use into something. And I close it. And let's just call the show method. Okay, it writes out the foo with name as expected. So let's move on and let's implement this for also for vector foo. So we will implement show for vector foo, which is very straightforward implementation because I can simply just loop through the elements. So for item in self, I just call item.show. And let's try this also. So let's see. We have this foo, and I will add another foo here. And no, it is good. Let's change the name to something like another, and let's save it and run it. And as we expected, it writes two lines out. Now what I want is that we are restricting the vector to be odd fools, but what we really want is to restrict only the trait. So instead of just writing foo here, we can use actually generics t template parameter, and I can define that this t should implement show, and that's all what I want. And because of this, I can implement show for every vector t where the t has the show implementation. So if let's say I will have also a car, and the car implements the show method, where to put that? Let's see, implement show for car. But this will not have name. This will have, for example, model. Let's implement the missing numbers, and let's print line that car with the model, and let's just give the model to the statement. Okay, so we implemented show for car also, and now this will work for cars too. So let's say this will be a car, this will also be a car, and without name and with the model. And indeed, it is working also. Now, what happens when, for example, I want to store both foods and cars? Well, one thing that I can do is to, well, at first, I want you to understand what is the problem with this. Like full name and car. The main problem here is that foo can have a different size than car, and the vector is a continuous storage, like a linear, well-defined so it is like you have in this, you have this structure in memory. So you have this zeros and ones, but you know this size, and after that the second element will have the same size. and so on. This is how vector is implemented. And because of that, vector cannot be used to store different types. So somehow we have to merge those types. One way to do this is using Rust enums. So for example, you have enum called, I will just call it foo and car. I'm not so creative. So let's implement this. So this is type that contains both foo and car. Actually, you can give a name, and you can also give, for example, any type. You can also specify a structure here, like something, and it's a name string. So you are not limited. And this is not a typical enum. In typical languages, the enum is just a number, basically. So in typical languages, you will see something like this. And you can specify index to basic types. But however, you can do that in Rust, or also you can do that in Rust. You can do even better things like storing structures in the enum variants. So it is a very great feature. And now I can use this. But the only difference is that foo and car didn't implement the show method, so we have to implement the show trait for foo and car. And it is really straightforward. Let's match self, which is the enum. So if this is an enum, I mean, this is an enum, we can match through the variants. And I can just fill the match arms, like this is foo. I will call it foo, and the car will be car. And let's just copy these names and I show. All right, so now it works again. So a foo with a name and car with a model. However, you also can use dynamic trait objects because currently it is more likely, it is a more strict structure. You actually have as large memory as you need to store for the largest variant. For example, if the car is very big, let's say 1 megabyte, then if you store a foo, then the foo will also be 1 megabyte because it is like union in the C language. So of course this works well for non-big types, so small types, but for others it is not really. But this is still a good feature and I like to use it much. But there are cases where it is just simpler to not using it. And this is simple. The way to do this is not making an enum. So I write these back, but instead I create a box. A box is like a pointer. So it will have a memory address, but the memory is will pointing to the heap. So this will not be stack memory anymore. So let's just do this. And no, this didn't solve the problem because we have a box foo and we have a box car, but they are just different types. So how to fix that? Well, we have to cast them in here as box dynamic show. So let's just make this. And we could store them as trait objects. This is called trait object. If you store a trait in the heap, then this is the trait object. Well, you can also store references, so it is not required to move to the heap, but we are creating those because it is simpler in most cases. And let's just implement show for the vector box dynamic show. So like this, but no, we don't have to use the T type here because we can also use dynamic show, or we can use just T here, which is the same. And it is maybe not enough. Then I have to use the T type. Or I don't have to use the T type. Dynamic show. No, it works. So let's run. This is about the same, although it is a bit slower because, as I said, this is using heap memory. Stack memory is a bit cheaper. But most languages use these anyways. And you are not noticing it. Rust is a bit more explicit than other languages, I have to say. Okay. Traits actually can be used for something else. So now we extended types with methods, but this can be also used like marking types, like for example, trait has engine, which is an empty trait, but this can be also used to like implement has engine for car. And now you can restrict types that you can only use a method that you can only use a method for types that has some engines. So this can also be used like this one. Okay. I think we should check some examples in the Rust standard library. So I'm not sure if you can see it well, but I will zoom it in. What is the most important trait in Rust is, I think, the iterator in std. Zoom it in so that you can see that. Basically, you have this iterator trait, and you can implement to any types. Let's see, for example, the implementation. It has an associated type item, which is used to decide what item we are using to iterating over. So, for example, if you have vector users, you have to specify item to user. And the only thing you should implement is the next method. All the other methods, and I think it is better to show like this, all the other methods are not required. They have default implementations. So if somebody wants to map over an iterator, they can do so, no problem at all, which is very useful. And for other languages, interfaces cannot have default implementation, which is well, not the best, I think. Or you can do abstract classes to provide default implementations. But in Rust, you can do it at once, which is very good, I think. And you can also override these methods. So, for example, there is a size hint which can be used for optimization. So instead of rewriting every method here, you can just optimize this iterator by just giving a size hint, which will be very useful for optimization. Okay, I think we can implement one. So let's see. Let's make a struct that is counter. And this counter has a previous element, which will be a U size. And let's implement the iterator with the item U size for counter. And let's just implement the missing members. The type will be, well, yes, we can just use the type definition here. Type will be U size, and the next will be an option self item. So, for example, if we start from 0, then we can actually just self previous element plus equals 1, and let's say return I have to store the previous value. So for example, the previous element will be this will be just the element, not the previous element. So first I store the actual element, and I increase the actual element, and now I return some actual. So this will be the next method. And let's try out. Or in counter that has the element, for example, this. I cannot initiate it here, so let's just move it to here, counter. Okay, and let's print the results. Of course, this would be an infinite loop, so we have to do something about it. Like we have a limit that is also U size, and if the actual is equals to limit, self-limit, then this will be just known. Or well, I can still print the limit, so it will be just limit plus 1, as this will be some actual. Okay, and now I have to add the limit also with 10 and run this. Of course, it runs as expected, so nothing interesting about it. But I can also use it because I made this iterator with, for example, map, and let's just find in this iterator or filter it. And I want every even number. And let's just collect it to vector. And after that, I just print it out. So let's see. It has a panic. Division by 0. I should have known that. And okay, just let's start from 1. What's the problem? it should be, this should be 2. Okay, no, this is fine, sorry. So yes, I just used an iterator method, and I didn't have to implement it. All right, let's move on, and we are at today's another topic, which is the macro. But before that, I'm curious if somebody has any questions about this.
So far we did not received any questions nor any message in the chat. If
All right.
any question, then feel free to ask in the Q&A chat or in the normal chat. Then David can hop in and answer on the fly. So yeah, I think we can move forward, David.
All right, thank you. So let's just create a main function. And in Rust, you see some weird named functions like print line, which has an exclamation mark in the end, or others like to do, which is similar, and like vector, which is a vec macro. So what are they? Of course, you could guess it, they are macros. Macros are basically, well, let me say in another way. Rust is a compiled language. And because of this, we have the possibility to just improve a bit the boilerplate. So for example, we could create a vector like numbers with this vector new and numbers dot push 1, push 2, push 3, and so on. So we could do that, but instead of this, we can improve the way how we write, and we can just use a macro that do this instead. So this is a great feature, and you can extend it if you want. Let me open a terminal, and I'm say cargo expand. It should compile. Yes, it compiles. But maybe the cargo expand is broken currently. Expand is not the official Rust tool. It is more likely unofficial package that can extend the cargo's functionality, but unfortunately I cannot show now. But anyways, if you would expand this macro, you will get similar to the previous implementation that I showed you. Okay, so how to implement macros? Because this is necessary sometimes. For example, hash map does not have this macro. So in hash map, you have to use the similar way to define it. Oh, this insert. Let's see. One is something, and the other one is something else. So this is not very nice to do. I would like to do something like hash map exclamation mark, and like one is the something and two is the something else. So in order to do that, we have a macro called macro rules, and this can be used to do this. And let's just add the name hash map, and no, it would work fine if I would delete this. I guess so. Maybe I should add something else to it. Anyways, just let's make it quick. For one item, I just comment this out. For one item, we should have E is an expression, and this sign, this arrow sign, and another one like value, which is another expression. And no, I think I deleted something else here. And yes, I should return something like hash map. Okay, that was a problem, but of course it needs some annotations. We can give them, but this will not be necessary later. For example, this will have a use size and a static star reference. All right. Then let's move on and let's validate another element. So for example, I create another one like something else, and there is a comma here, and the index will be different. And let's just do this, which is marking that this will be a loop. It is basically similar to the regaps, but this is not exactly regaps. So you have differences like this. Comma means that this is a list with list separated by commas, and this plus sign marking that repetition should be at least once. But this could be also many more. If I change to star, that would mean that this repetition will allow empty elements. So for example, no elements. All right, there is a hash map here. Now we can actually populate this hash map, but this curly brackets is like for keeping the things inside together. So what you see here, this will be replaced to here. So instead of doing this, we should add another curly bracket. So when I paste this to here, this would make sense. You can just add as many curly brackets as you want. Rust will return the last unclosed statement. So this is not a problem in Rust, and we are using it a lot of times. So we have this another curly bracket. Let's make this hash map, and let's return it at the end of the statement. All right, and let's add the elements. And what I do is basically the same as I defined it above. So first I give the repetition, and here I say hash map, but insert, and we can use the key and value. And I should close it. But hash map is not mutable, so I have to do it. Have to make it mutable. And no, I don't have to write this hash map type because it is automatically determined from the usage. All right, and this is indeed working. So if I just print it out, like this, that I could see the result. So yes, it is a bit less readable, I have to admit it, but after you have already created, for example, 10 macro rules, it is not really hard to read. And as you can see, this is not a Rust code here. This is the language that we define. So actually, we can do many things here, although there are some limitations, and these limitations are for good reason. This is semantically not Rust, but the symbols and some of the grammars are applying here. So you cannot do anything in here. And there are other rules that you can, for example, if you have a variable here, you cannot use that inside the hash map if you are not passing it to the macro. So if you pass it, you can use that. So there are some not safety features, but hygienic features. This is also called as macro hygienic. So yes, this is pretty cool, and you can define your own language which will have syntax highlighting, and indeed you can write, for example, this key is an expression. What does it mean? It means that you can technically write any expression here, like 1 times 2, which is a valid expression. And there are other meta types in the macro rules, like patterns, visibility, symbols like pub, rate, and so on. So this is very good to have that, and also very interesting to use. And there are projects that, for example, there is a Rust project that implemented a Python way to process arrays. I don't know if I can find that. Oh, you can even write Python in Rust. That's pretty amazing, I think. But of course, it is not needed. And if you can write Rust in the code, that is always better than using macros. Okay, there are other types of macros which are not macro rules, but something called procedural macro. Procedural macro are more advanced macros. Basically, procedural macros can take tokens, like this is a token, this is also a token, this is also a token, and so on. So there will be a list of tokens, and it can process the tokens and produce different tokens. To show this, I think you almost seen that for some structs, we use this derive here. For example, for deriving debug. And these are amazing. Things in Rust, you can just auto-implement a trait for a specific struct by just passing this derived word, and this will implement that based on the fields it has. For example, let's see, it has a name, which is a string, and I could just write out this name string from hello, and this works. So this derive here is a procedural macro, and what it does is basically reading the tokens here. So for example, this will determine that this is a struct. Okay, so we will use this implementation for a struct, and this is necessary because, for example, for an enum the implementation would be different. or like for other types. And it can also determine the name and so on and so on. I will not show you how to implement procedural macro because that is a bit advanced, but I will show you one of my implementation, which is, I think it is very interesting. So let's find. All right, let's just open VS Code here. I close this one. Basically, I wanted to create a framework that is similar to the JSON server, if you are familiar with that. JSON server is a mock-up backend that basically can use a JSON file for storing data. So it doesn't need a database. So I wanted to do a framework, and for example, I created a struct app state, and I want that to be able to just auto-generate some code that I could use for CRUD endpoints. So I created a derived memory DB. Memory DB is a trait. I can show you. I think I close this one. Okay, so here it is, the memory DB. And this is pretty straightforward trait, so nothing special in it. It doesn't even do anything. So let's just move on and see what does the derive do. Here it is, the derive model method that I use, and basically what I have to do is write above that this is a derivable. This is a method for the derivable memory DB trait. So this is how it should understand the Rust code. And as you can see here, you don't have to manually parse the Rust syntax because it is really straightforward to just use a package, and we can be sure that that package will have the correct Rust syntax that we shouldn't be worried about. So this parse macro input will just parse the token stream that I have talked about, and I can just get the struct name by input.ident, and for example, I also can get the fields, and there are fields that are named, and for other fields that are not named, I can just throw an unimplemented error. And I got the named fields, and basically at the end of the macro I can paste the Rust code after the struct, and this is very good because this is actually the implementation for the memory DB. As you can see here, we implement the memory DB for every subtypes. So yes, it is bit hard to read, and I have said that this is advanced Rust, but it is very cool for, not for applications, it is more likely for packages, where you want to provide some easy way to do things that you use a lot, so you don't have to type these implementations again and again. And this is very straightforward. And what happens after? So for example, you have created app state with MemoryDB, and you can just expand it. And because you have expanded the MemoryDB derive, you can just copy and paste it here and modify the original behavior. So unlike, for example, the JSON server that I've talked about, we can actually modify the behavior here at a very low level. Let me show you another good crate, and this will be the last thing that I will be talk about. I will talk about. And for this, I think I go back to Rust Learning here. Just like so. Okay. And let's just add the dependency. And this is how you install packages in Rust. There's a page that you can use to find packages, but if you know the name, you just type. I know it is Sherda or Sherda. I don't know how to pronounce it, but I add it. And as you can see, the Rust analyzer already working on getting that package because I saved the cargo.toml. So now we can use the Serbi. I will call it Serbi. I hope this is how it should be pronounced. And I will add serialize and deserialize. And these are traits that I can derive. And let's just create a user with a name string and email string or age inserted. Well, U8. 8-bit and unsigned integer will be enough, I think. And let's derive these things. So let's just derive serialize and serialize. It should be good, so I check it instead. Okay, no, I don't really need set there because it is enough to just have the set.json. And that's it. It works. Okay, or not? Not yet. I think I need both. Yes. So I need set also. All right. And I think it is having a feature to use the derived macros. Let me just see this. Ah, yes, I have to pass the feature. Also, this is also very cool in Rust, but that but you don't need, you don't have to use it. So if you have a package that can do a lot of stuff, then you can just select what you need. So let's save it and know it will work. Right. And now I think I just copy and paste it here because this will be much easier. So let's create the user. With the name David into and with the age, well, I don't know. Let it be like that. And what we can do here is basically now we can create a string from this from the structure in a JSON form. So this will be JSON here, and you can also deserialize it, and you get back a user. But I also did write debug in order to be able to print it out. So let's just write it here. And as you can see, the serialized one is the JSON format that this set.json did. But we can also use for this set library for YAML and other formats, and this will be statically typed unless, not unless, unlike in other languages where, for example, you can load JSON file, but you cannot type it, or you can type it, but the compiler cannot value or cannot validate at compile time. Well, here the Rust also can Rust cannot do the theta, but what you get here is the final structure. So if SERDA cannot do something, for example, SERDA cannot parse the age, then this will be a panic. and that's the expected behavior. So I think it is very cool. And you don't have to derive, for example, JSON serialize and JSON deserialize. You just derive serialize and deserialize, and you can use serd as any other libraries like serd YAML or serd toml, XML, and others. So for a backend, this is a very useful feature. And as you could see, it is not impossible to implement derivable procedural macro. Okay. So thanks for watching, and this was the last thought that I wanted to share. So if there are any questions, I could answer them.